Okay, today we focus on brain network analysis. One of the approach we called independent component analysis, or in short, ICA. This is one of the famous methods that can perform so-called data-driven brain network analysis. So we will talk about this today. Again, please visit my website, this link, and please download today's handout and materials. The size of the materials zip file is a little bit big today. Actually, it's around 200 or 100 megabytes. So please do take time and download the data right now. And today we are going to use another toolbox called GIFT. The full name is Group ICA of fMRI toolbox. Again, with the first letter of each term. So GIFT in short, GIFT. GIFT toolbox is one of the MATLAB toolbox that can help you using user-friendly GUI to perform so-called group ICA analysis based on the fMRI data. The fMRI data can be either task-specific data or even the racing state data. That would be fine because ICA is one of the data-driven approach. You don't really need a model to perform the analysis like the GLM or something. So you don't really need any prior information for your data set. However, you do need to perform all the necessary pre-processing steps, including slice timing, realignment, maybe the normalization, smoothing, and bias correction. You still need to perform all the necessary pre-processing steps before you're using this ICA analysis. Okay, so you can use SPM or even the FSL or something. Just finish all the pre-processing steps and input the pre-processed data into this toolbox will be fine. Okay, so again, please visit this website and download I think the newest version should be version 4.0b. I think this is the newest version. So please go visit the website and download the file. I'd like to again remind you that GIFT toolbox is actually one of the toolboxes using the SPM, actually the file selection function. So again, if your file path include the Chinese character or space, please try to modify your the file name. Do not include any Chinese characters or space, or it may cause the error. Okay. And another thing, from the MIA lab, they provide two versions of the GIFT toolbox. One is directly from their website, and another is from the GitHub. But be very aware of this point. They claim that these two packages or these two versions are identical, but actually they are not. The package from the GitHub is actually incomplete. They miss so many different functions, and some of them are critical ones. So please do not download GitHub version. Just download this package, Group ICAT version 4.0b .zip file directly from their website. Do not download from GitHub. Okay. So today, as we mentioned before, fMRI analysis including three different types. And we already spent several weeks talking about how to perform the brain activation analysis, either using the SPM or so-called DPABI or DPARS toolbox to do the ALFF or ReHo calculation. So today we are going to talk about the second part, the brain connectivity. So in general, brain connectivity is an approach that actually measure or estimate the dependencies of both signals between brain regions or between voxels. You'd like to find out whether a cluster or a group of voxels may exhibit similar mode pattern. If yes, you may gather them into one network to say they may perform or they may collaborate with each other to fulfill the brain function. Otherwise, you may using the correlation analysis using one of the voxel or a small spherical region as the seed point to calculate the correlation coefficient between this seed point with other brain regions. Okay, but today the ICA independent component analysis is actually one of the approach to help you cluster the brain regions into several different networks. Okay, so this is what we are going to talk about today. And I again just leave this slide for you so you can just check all the image parameters that we used to acquire the data set that I provided for you today. Okay, so again we use our university. We use the 3D scanner in our university and gradient EPI data set with TR 2 millisecond, and the original matrix should say the original spatial resolution is around 3 by 3. This one 3.4 by 3.4 by 3.4. Okay, and the slice number should be 40. And today I actually provide I think 2 data sets of the motor tasking fMRI. Okay, so we actually designed a task with 10 blocks that we ask a participant or the patient to perform the hand grasping. Okay, so this is the data set that I provided you today. So in the first session, I'd like to talk about the ICA, the principle behind the ICA, and how can we use this analysis approach to analyze our fMRI data set. So as we mentioned in the last week, normally for the task-specific fMRI, we can perform either the model-based analysis, such as the GLM, but also we can consider some approach called model-free or data-driven analysis. And that means you don't really need to set up the model. You don't really need to understand what kind of the experimental design behind this data set. You can use this way to do so. In the last week, we actually used the PABI toolbox to perform so-called data-driven analysis on the resting state fMRI. And today we are talking about the ICA. Actually, ICA can perform on both task-specific fMRI as well as the resting state fMRI. Okay. However, the data set I provided for you is actually one of the task-specific fMRI right here. So this is what I mentioned in the last week, that the resting state fMRI analysis can generally categorize into 2 different types. The first one is the way to depict local features, such as the ReHo and the ALFF. Okay, and today we are talking about this one, independent component analysis. This is one of the approach in the functional quantitative analysis right here. Okay, so you need to understand that when we learn a new approach or a new method, you need to really understand what kind of the scenario that you can use this kind of analysis. Okay, and the ICA is actually a pretty famous and pretty historical method that actually developed in around the 1990, and it's originally applied for the signal analysis. Sometimes when we talk about some, you can have some audience or some brain activity, for example, the EEG signals, you can try to use the ICA analysis to extract the source signals or the original signals behind this kind of a mixed signal. And until I think 2000, around 2001, there is a first group starting to think about maybe we can apply ICA to the fMRI data set. Okay. So let's start from the very beginning example that actually generated for the signal analysis. So let's think about this famous example. We called a cocktail party problem. Okay. For example, in this cocktail party problem, you have a group of people talking about something. They may be discussing something. The most important thing is that these 3 people are actually speaking simultaneously. They just speak in the same time. And now in the party, you actually have 3 different microphones located in different corners. And as you can see in this picture, these 3 different microphones actually has different distance to different speaker. For example, the first one right here, the left-hand side, this one, actually is more close to this one. It's closer to this speaker, and to this one is a little bit far, okay? However, to this one, actually, this microphone is closer to this one rather than this one, okay? So now what you can imagine is if I try to record the sound from these three different microphones, actually the weighting from different speakers would be very different. For this one, actually the largest sound or most clear sound is actually from this one, okay? So the distance would be become one of the weighting that you can have the mixed signal from these three different microphones, but you are going to think about, is there any way, if I only have the signals from these three microphones, do I have any way to reconstruct so-called source signal? That means if I can reconstruct the audio signals from each of the speaker. I don't want the mixed signal, I want the pure signal, we call the source signal. In this point, we actually try to model this kind of scenario using this kind of linear combination right here. You can see we put the measurement, that means the signal from these three different microphones, as the x1, x2, and x3. Of course, this is the audio wave that actually changed with time. So this is a function of time. The t means time, okay? So you can see right here, we assume that there are three different sources. This is the thing you need to assume. We have three speakers, so I assume that there is three different sources right here. So S1 represents the speaker 1, S2 is speaker 2, and S3 is the speaker 3 right here. Okay, so you can see that three different microphones actually have different linear combination from these three different sources right here. So for the first one, actually the speaker 1, this one, may have the largest weighting right here, 0.7. But for the right-hand side, this one may have the smallest weighting right here, 0.1. However, for the microphone 3, it may have the reversed weighting right here, so you can see. However, in the real scenario, what you can get on hand is actually only these three measurements. You don't know what is the original speaker is talking about, and you also don't know what is the weighting. You may say that maybe distance is a good weighting for this kind of linear combination, but to be very honest, not that easy, not that simple. So you cannot directly use the distance as the weighting. By using distance as weighting, you may, I don't know, just cannot reconstruct a very good source signal right here. So now the problem would be the only known measurement is on the left-hand side. However, for the right-hand side, 9 different parameters right here, and the 3 different source signals right here are unknown. So this is kind of the problem. We say this is the blind source separation issue. We only have the mixed signal right here, but we don't know source, we don't know the weighting. We need to solve this kind of problem. So this problem, sometimes we say in abbreviation, we may say the BSS problem, blind source separation problem right here. We can rewrite these 3 equations into a matrix form right here. So we may put all the measurements right here. Sometimes you may have measurements more than 3. So you may have the x1, x2 to xm right here, if you have m measurements right here. For the right-hand side, again, you can assume that you have several different sources right here. It's not necessarily to be 3, it can be more. But there is a very important criteria right here. The sources that you assume, the number of the sources you assume, cannot exceed the number of the measurement. If you only have, for example, 3 microphones right here, you cannot say, I'm going to try to resolve or reconstruct the source signals more than 3. It's not possible because you only have the 3 measurements. Okay, so this is kind of the limitation of criteria right here. Or right here, you can say that the m, the small m right here, should be at least equal or larger than the k right here. K is the number of the sources right here. So this is in matrix form is the x equals to equals a multiplied by S. And what is A? A is actually the mixing matrix, or you can say A is actually the collection of all the different weighted variables here. Okay, so this is the mixing matrix right here. However, you can only have these things on hand, the major signal. And this part, these two different unknown variables are the things that you'd like to estimate and reconstruct it. So now we try to transform this kind of the cocktail party situation into the fMRI situation right here. So you can see now what we have right now is not microphones. What we have right now is actually the profile, the bold profile from each voxel. Okay. So now you can see we have plenty measurements right here. We may have over 10,000 voxels within the fMRI imaging dataset. That means we have over 10,000 measurements right here. Of course, the measurement now is both profile or both signal right now. And what we are going to do is we'd like to reconstruct the source. But now the source is the network. It's a brand network. As you can see right here, normally we say we'd like to have source that actually independent to each other. Okay. In this case, when we say this is a spatial ACA for fMRI, that means we'd like to reconstruct the source network that actually spatially independent with each other. That means non-overlapping network right here. So as you can see right here, if we can reconstruct three networks right here, you can see this is the motor networks in the upper slice right there, and the deformal network, this is the medial prefrontal cortex right here. Visual network more likely located in the occipital cortex right here. So as you can see right here, we have three non-overlapping or spatially independent networks right here. So you can see right now, this is the sources that we like to estimate. And of course, you need to estimate how this kind of these three networks may mix up with each other to create the real or to create the estimated Baud signal right here. So this lines right here is pretty similar to the fully connected neural network, but not. This is actually the relationships between the original source networks and the measured Baud signals right here. Okay. So again, now the limitation would become that the number of voxels should be larger or at least equals number of the networks. However, in fMRI, it's very easy to fulfill this kind of the criteria because the image may contain, I think, easily contain over 10,000 voxels. So you won't always seek for 10,000 different networks in a brain. This is just too many. So normally we will try to reconstruct, I think, around 20 to 30 different networks within a brain network. So within a brain imaging. So I think this criteria would not be a problem for the fMRI dataset. So now I try to rewrite the equation right here. As you can see, I just transform the matrix form into this kind of the equation right here. So X right now is actually the collection of all the Baud signals from all the major voxels right here. So we say X is actually the fMRI data. Okay, and on your right hand side, again you have A and S right here. Again, S is a collection of the sources. Right now we say this is the maximally. Of course, you cannot claim this is really data independent. We can only say that we use some algorithm try to maximize the spatial independence. Okay, so now we say this source should be maximally spatially independent networks right here. Okay, and this A mixing matrix again, however, would become the time courses of the sources. Sometimes we will say, if you use the ICA, this kind of the mixing matrix, sometimes we will say this is the IC signal, independent component signal. Or sometimes you just say this is the mixing matrix right here. So for each network right here, for example, we have three independent networks right here, motor, deformal, and visual networks right here. You will have three corresponding time courses right here. And these time courses is actually kind of the representation of the mean or average, but not really the mean or average. It's kind of the representative signals for each network right here. So you can see, for example, this is the motor network, and you can see the time course, the IC signal or time course right here is pretty similar to what we designed for this fMRI data set. Actually 10 blocks for the motor grasping. So you can count, there's 1 block, 2, 3, 4, 5, 6, 7, 8, 9, 10. Actually, you can identify this kind of the time courses for these 3 different sources or 3 different networks right there. Okay, so this is the rephrase or the reform of the ICA that you apply original independent component analysis for this single problem, but now you can apply this to the fMRI. So you can see this is the issue that we're going to seek for. We only have the fMRI data on hand, but now we'd like to reconstruct both the source networks and the corresponding time course right here. However, if you try to search for ICA literatures or some publication for the fMRI, you may find out that actually ICA can be categorized into 2 different types. The first one would be the one that we just introduced, spatial ICA. But another one, you may see this term, temporal ICA. Temporal ICA. However, I have to say that the spatial ICA still be by far the most common approach that we applied to fMRI data set. So in this week, I will only focus on this one. However, for the toolbox that we are going to use today, the gift, also provide the possibility that you can perform the temporal ICA for the fMRI data set. And you can try to compare the goal for these 2 different ICA types. The first one, spatial ICA, is actually trying to identify the independent components, or we say the brain networks that actually have the maximized independence in space. Okay, that means spatially independent or non-overlapping brain network. This is the one that we call spatial ICA. For temporal ICA, it's a little bit hard to imagine because it's actually trying to estimate the independent components that actually have the maximized independence in time. It's pretty hard for us to imagine what is this. So if you're really interested in this category, you can try to read some paper and try to figure out what does this kind of temporal ICA represent. However, today we focus on this because I think more than 80 to 90% paper using ICA is talking about the spatial ICA. And as you can imagine that sometimes or most of the time that actually we will collect several different or multiple subjects for one study. So there is a term that called group-wise ICA. You can easily apply the ICA for a single subject, just what we displayed right here. You can see for one single fMRI data set right here, you can perform the ICA and try to identify the potential independent network right here. However, if you have a group data set right here, that means you may have 10 or 20 or 30 subjects data on hand. Can you perform the so-called group-wise ICA? That, of course, yes, you can do so. And this is one of the approach that you can do so. We call the concatenated ICA. Why we name this ICA in this way is actually we just try to concatenate all the fMRI data set from different subjects into a full matrix right here. So you can see for first part, it's labeled as the fMRI data 1. That means the fMRI data set from the first subject. And then as you can see right here, we didn't put the original fMRI data in this matrix. Actually, we reformed the matrix. You can see right here, the rows represent the time point right here. For example, we collect the motor task fMRI data for maybe 200 followers right there. 200 followers with TR equals 2, that means you have 400 second data set right here. So rows, each row represent a time frame or the time point right here. So you can see if we have 200 followers, then you have 200 rows right here for one subject. And the focus right here, of course, we will only consider the voxels within the brain region. We won't consider the voxels from the background or from the skull or scalp. We don't think about this. We focus on the voxels from the brain regions. So as we may take the practice for the second part, you will see that actually GIFT toolbox will automatically generate so-called brain mask for you. And they will, the toolbox will focus on this region, the voxels from this region to perform the IC analysis. So you can see we will transform the original image-wise, the fMRI data, into this kind of a matrix that rows represent time, columns represent the voxels. So you may have over 10,000 voxels right here, okay? But again, now you can see we will have the fMRI data 2 right here. So now this means we have the fMRI data from the second subject. Again, you will have the same, you definitely need to have the same time point. So for each, you will have 200. Again, you definitely need to have the same voxel number right here. So what you're going to do, you will use the same brain mask for the second subject. So again, if for first one you have 10,000 voxels, you definitely need to have the 10,000 voxels for the second subject. So you can really concatenate the data set into 4 matrices right here. So you can concatenate the data set as many as the number of the subject you collected right there. Okay. And what I'm going to do is now you can see the X right here is this one. So I may write down X right here. It's not something wrong. No, it's just X right here. Okay. And this one is the things that we talk about is A, the mixing matrix right here, right? And this one is the source signals right here. And again, we said we are using the spatial ICA. So this one is actually, we called group ICA because we use the group data set right here. We can try to reconstruct the now overlapped brain networks right here. So visual, DMN, deformal network, and motor network right here. And again, this one we call group time courses right here. This is a mixing matrix or just the time course that I showed in this slide. Okay, so by concatenating all the data together, you can just create so-called group-wise ICM maps. That means this kind of a brain network is not estimated from single subject, but actually this kind of a group ICA can be used to represent the common brain networks that you can actually extract based on the whole data set. Okay. However, sometimes if you'd like to perform some statistical analysis, you still need the subject ICA data on hand. So you can perform the statistical analysis, right? So what you can do right now is you need to do so-called reconstruction. And one of the famous methods is so-called dual regression. Dual means 2 times, double times. Okay. So you can see dual regression right here is actually composed of 2 different steps. The first step is right here. Now, if you successfully perform the group-wise ICA and you have the group ICA maps on hand, now what you're going to do is you try to reconstruct the subject ICA map. So what you're going to do right now is now you replace the left-hand side. Now you only put the fMRI data for the specific subject. For example, now you focus on the subject I. So now you only put the fMRI data set right here. And again, this one is actually the group ICA that you actually obtained or measured using the group-wise data set right here. So these 2 things are known. Okay, this is what you have on hand. This one is actually unknown variable that you need to calculate. However, with this equation, actually you simply need to perform the GLN to get this kind of time courses. It's not that hard. So that is what you are going to do. Now what you can get is you can use the group ICA and the subject data set to obtain the subject time courses. Again, you may have this kind of time courses based on the group data set. But can you have the subject time courses on hand? Of course, just use the first step of the dual regression. So this one is sometimes we called subject time course right here. Okay, so this is not the group time course. It's a little bit different because you only use the subject data set to estimate this kind of time course. And then final question would be, can I obtain the subject ICA map on hand? Then now you see why this is called dual regression, because for the first part I performed regression for once, and for the second step I just perform another regression. However, now again I put the fMRI data right here, and this is the time course that you just obtained right here. Okay, now you can use again the same data set for this subject I, and you have the subject time course on hand. Now you can again perform another regression or GLM right here. So you can see now what you have on hand is actually the subject ICA components. It will be a little bit different from the grouped ICA map. However, you can compare this later. You can see if you have all the subject ICA components or ICA maps on hand for each subject, then you will have the chance to perform the statistical analysis. You can determine whether a group of the people, for example, the healthy controls people and the patient controls people, may have the similar or different spatial maps if you have each of the maps on hand. Okay. So this is so-called dual regression approach that can help you reconstruct the subject ICA from the group ICA result. Okay. And based on one of the papers, this is actually a paper from the PNAS. I think this is a very important journal that I think only if you can get a recommendation from the some famous scholars from US, then you can publish paper in the PNAS. Okay, but in 2006, actually, they published a paper called "Consistent Racing State Networks Across Healthy Subjects." So I try to introduce this paper to you just for your reference that actually ICA can definitely perform on the racing state fMRI. Not only for the task-specific fMRI, but for the racing state fMRI, you can use the ICA. And actually, this important publication is actually now cited for more than 3,200 times. So this is very important. And however, this paper didn't do a large population study. They actually only collect 20 subjects fMRI data set and perform the ICA analysis right there. However, they try to identify, is there consistent pattern that we can observe across different subjects to say we have consistent pattern for the racing state brain networks. Okay, so sometimes we now say racing state network as the RSN. Okay, with S, that means you have multiple networks right here. So as displayed in this figure, you can see. Okay, you can see they identify 10 different networks that are consistent with within these 20 subjects right here. So first one would be the visual cortex. You can see this located mostly in the lateral cortex right here. Okay, and this one again is a very important part for the racing state fMRI. That is the deformal network right here. So you can see. Again, this pattern, you definitely need to remember this pattern. For the precuneus, along with the post-cingulate cortex and the medial prefrontal cortex right here. And sometimes you can see some supramarginal or angular region, or you can say superior parietal region right here. This is the pattern of the DMN right here. Okay. And for the C and D, they are actually the related to the memory function, the network related to the memory function right here. So it's separated into two different components: C for the right hand side and D for the left hand side right here. Okay, and E again, it's actually are again in the visual cortex right here. However, this is more located in the medial part. For the A component, it's actually in the lateral part right here. And for the F, this is the motor cortex right here, motor network right here. However, this motor network didn't identify any SMA region, only I think mostly the primary motor area right here. So you can see this is the, sometimes we call motor network or sensory motor cortex right there. And I come to the G. G is actually the ventral string of the visual processing. Actually, this is the occipital temporal pathway right here. So you can see this is the visual cortex, and this small part is actually located in the temporal lobe right here. So sometimes we say this is the occipital temporal pathway. We have a ventral system, and we also have another dorsal system right here. Okay. And for H, this is the superior parietal cortex. For I, this is very important when you say this is located in the superior temporal gyrus right here. So this is highly correlated to the auditory function right here. And another one is the executive control and working memory for J. So at least these 10 networks based on the resting state data from 20 different subjects, they can consistently identify these things using the IC approach. So I think this is just another example that you can use either resting state data or test-specific data. You can use either way, just try to apply the IC on it. Okay.